Hello everyone, and welcome to the second part of our lecture series on synchrotron radiation. In the first part of the series, we talked about what synchrotron radiation is and where it is found in the universe. Synchrotron radiation is a radiation produced by a charged particle in a magnetic field, a relativistic or fast-moving charged particle doing spiral motions in the magnetic field. And again, a charged particle, when it accelerates, it produces radiation, and in this particular case is known as synchrotron radiation. We talked about how synchrotron radiation is ubiquitous in the universe. It's found wherever there are astrophysical plasmas and fast-moving particles, and wherever there are magnetic fields. Then we started talking about the relevant equations for synchrotron radiation. We started with the discussion of the dynamics of synchrotron radiation. And for dynamics, we have now a charged particle in a magnetic field. It experiences the Lorentz force, and it does circles with a angular frequency omega g or omega b, depending on which book you read, which is qb over gamma m, where q is the charge in the particle, b is the magnetic field, gamma is its Lorentz factor, and m is the mass of the particle, or nu g, which is the corresponding linear frequency. Then we derived the radiation power that this particle will emit, and that required using Larmor's formula, which tells us the radiation produced by a charged particle undergoing some acceleration. We had to do a couple of Lorentz transformations to do that, and we found the radiation power is given by this formula, where we have the Thomson cross-section of that particle. Remember, that depends upon the mass of the particle. So if you have different kinds of particles, that expression, that value is going to be different. The speed of light, beta and gamma, are the speed relative to the speed of light, and gamma, of course, the Lorentz factor of the particle, and then the magnetic energy density. So this tells us how much energy the particle will radiate as a function of time. Then we were interested to know what is the spectrum of radiation that the single particle produces. This requires doing a Fourier transform, and it also involves some light travel time effects. So we did some geometry, and we determined that there is a characteristic frequency of this radiation, which is this omega c, where c stands for characteristic here, which is a function of the Lorentz factor of the particle, and that is now is hit by this factor of gamma cubed because of this these relativistic time travel effects. And so at the end of the day, the characteristic frequency of the charged particle is proportional to gamma squared. And so, as a reminder, both the power and the characteristic frequency are proportional to gamma squared, and both of these become relevant when we discuss synchrotron cooling, for instance. And this particular one becomes relevant today when we talk about the synchrotron radiation from a distribution of charged particles. Then we derived the actual radiation spectrum. So this is just the characteristic frequency, but it has a full spectrum. We derived that spectrum, or I wrote down an expression for it. There are two components. There's the perpendicular and parallel components, the two polarizations of synchrotron radiation, and the total power or the total emissivity is given by this expression, where now I'm assuming that the radiating particle is an electron, and so I put in E and M for the electron. And then there's this synchrotron F function, which comes about from various integrations, and it's just basically a form of the Bessel function, and it has this asymptotic solution, or asymptotic form, where it rises as x to the 1/3, where x is its argument, peaks at some location about 1, and then it falls off exponentially. So this is a recap of our discussion from the first part of the lecture series. If you haven't seen those videos yet, feel free to pause this video here, go back through those, and until you feel comfortable with these concepts, because all of these concepts, especially this one here, is going to be really important as we discuss the radiation spectrum from a distribution of particles. Alright, so with the understanding that you're familiar with this, we're going to proceed today in the second half of, or second part of this lecture series, and we're going to talk about the radiation spectrum from a power law distribution of particles. Now, why is this relevant? It's because in any given physical situation, we can't expect to have just a single particle radiating, right? You'll have a distribution of particles, they may have different energies, and in particular in astrophysics, there is a very common distribution of particles, which is a power law distribution. So a power law distribution, also known in statistics as a Pareto distribution, though you will not hear astronomers call it that very frequently, just means that the number of particles as a function of the Lorentz factor, d and d gamma, is a power law, gamma to, let's say, some power p minus p as a function of the Lorentz factor gamma. And so here, of course, this is a log-log plot, and we assume that there is a lower cutoff. This will become relevant in a bit, and we assume that this distribution extends off to infinity. So why power laws? Well, it turns out that power laws are ubiquitous in astrophysics. They show up in all sorts of places. There are in fact papers on why there are power laws, or so many power laws in astronomy everywhere. We don't fully understand this, but it's sort of a reverse or chicken and egg sort of situation where we'll see that the radiation spectrum from this distribution of particles itself is a power law, and that's the theoretical framework. But then if you look at observations, we see that the radiation spectrum, synchrotron radiation spectrum from astrophysical sources is a power law. And so we infer that actually what is producing the radiation must involve a power law distribution of particles as well. And so of course now there's theory as to how these particles get accelerated into these power law distributions, because these are now relativistic particles. And that's a whole other research field and whole other set of lectures that we can get to another time. But for now, we're going to assume that magically we have this distribution of particles in a volume of space. They follow this power law distribution. It's truncated at some minimum Lorentz factor. And we won't go over this, but you require this truncation because otherwise you get infinite energy in this system. So you need to truncate it at some lower Lorentz factor. And this will actually have observational consequences, this truncation. And in fact, people, just as an aside, try to go ahead and measure or infer this minimum Lorentz factor by doing observations. Okay, so let us continue our discussion of synchrotron radiation from a power law distribution of particles. Just as a note, if you're taking this as part of a lecture series, at various points in this video and subsequent videos, I may pause and ask you to consider something or derive something or calculate something. I would encourage you to go ahead and do that. I think it will enhance your learning, but then it depends on the particular context in which you're observing or watching this. Okay, so let us make this a little more, let's say, specific. And we're going to say that this dNt gamma, which I've just drawn down here, has this following form. So dNt gamma, mathematically, is some constant, some normalization constant n naught times gamma to the minus p, as long as our gamma is between, let's say, gamma 1 and gamma 2. So I'm going to relabel these Lorentz factors here, and I'm going to call this minimum gamma 1 and this maximum gamma 2. So there's a power law distribution, and that it is 0 otherwise. So there are two regimes, so in between here it's a power law, and everywhere else there are no electrons at any other Lorentz factor. Now just note that some authors, instead of having power law distributions in Lorentz factors, they have power law distributions in electron energy. And electron energy is gamma mc squared, of course. And so at the end of the day, the formulae that they have, Malcolm Longair's high energy astrophysics is a notable example, will have various factors of mc squared to various powers of p running around. So if you find m to the power of some random factor of p, don't be alarmed. It comes about because they're assuming that it's power law distributions in energy rather than in these Lorentz factors. But it's effectively the same. There is another thing to keep in mind, which is that we're going to assume, we're going to focus on the ultra-relativistic case. So we're going to assume that our Lorentz factors, gamma, for these electrons are much greater than 1, or correspondingly, beta is of the order 1. This is for the electron Lorentz factors. And in fact, this is often the case for astrophysical situations. And that's because frequently the value of this gamma 1 is at least the order of mp over me, the proton to the electron mass, and this comes about from relativistic shock physics, which is often where these electrons get accelerated. But let's not worry about that for now. So frequently this is quite a bit larger than 1, so you can assume that. In cases where that is not true, which is for instance in non-relativistic shocks, or like say the magnetic poles of planets, that sort of scenarios, you need to relax this assumption, and then it's better, instead of having power law distributions in Lorentz factor, to have power law distributions in momentum. And then you can account for these particles having momentum all the way down into the non-relativistic regime. Right. So often, like in relativistic astrophysics, you may find that you are kind of straddling that regime, and then some of the stuff that we discussed today may not be applicable. So just be careful applying the results into those trans-relativistic regimes, and just check whether you're in the appropriate regime or not. So what we're going to do is we're going to calculate the radiation spectrum from this distribution of particles. And to calculate the spectrum, we're going to assume that each electron radiates at its characteristic frequency. So we're going to assume that this synchrotron F function is sharply peaked, or we're going to make use of the fact that it's kind of narrowly peaked around 1, or of the order of 1. So we're going to assume that each electron or Lorentz factor gamma produces most of its radiation at this characteristic frequency omega c. And mathematically that will take the form of just writing this as a delta function at omega c. And so the total radiation spectrum is going to be the superposition of the radiation produced by each of these particles at their own Lorentz factors, radiating this spectrum but narrowly peaked, and we're going to add up all of that, and we're going to see what the final radiation spectrum looks like. And spoiler alert, it's just going to end up becoming a power law as well. So there are a couple of ways to do this. There's the easy way and there's the hard way. And the easy way requires us to just get some physical insight, and we're going to start with that. And then the hard way is kind of more mathematically rigorous. It'll give us the same result, but it requires actually doing the full integration. And some of that I'm going to do for you, and some of that I'm going to leave for you as an exercise. So let's start with the simpler or the intuitive kind of framework here. So as I said, we are assuming that the radiation from each particle, each electron in here, is sharply peaked at this omega c. And so the spectral power, P omega, in some spectral range d omega, is going to be equal to the number of particles that are radiating for a given Lorentz factor times the distribution times the width d gamma, multiplied by P of gamma. So what did I do here? I'm assuming that each particle that has a Lorentz factor gamma is producing this much power. There are these many of those electrons, and all of that radiation appears in this narrow frequency range d omega, and so it contributes to the power in that range. Right? So that's how this expression comes about. So if this doesn't make sense to you, stop for a moment, make sure you understand this, because this is after this, the rest is just algebra. Okay, so with this understanding, this is, to put a final point on it, this is the radiated power in some narrow frequency interval d omega. This is the number of electrons that are radiating into that d omega, and this is the power per electron of Lorentz factor gamma. And again, we're assuming all this power goes into a narrow frequency interval around the characteristic omega c of that gamma. So then, this P of omega, just looking at this expression, is P gamma times d and d gamma times d gamma d omega, and I've just taken the d omega to the right hand side. And now let's look at how each of these depend upon the Lorentz factor. Right, so P gamma as a function of gamma is clear. It's also on the board. So I'm going to let you think about what each of these is, and then feel free to pause this video for a moment and check that you know how each of these depend upon gamma. So P gamma is proportional to, as we have up here, gamma squared. And then d and d gamma, we have down here, is proportional to gamma to the minus p. And that leaves us d gamma d omega. So what is this d gamma d omega? So the way to figure this out is to understand that what is going on again is that we have for each, let's say we're looking at a particular, let's say this is our gamma axis, and we have a certain range d gamma in here. These are the electrons that we are considering in this expression here, and they are radiating within some range d omega. So these electrons are radiating into this interval d omega. Then how are these d gammas and d omegas related to each other? And that, of course, is now straightforward to understand, because each electron at Lorentz factor gamma is radiating into its corresponding omega c. Right, so all we need to do is transform this gamma into this d omega using this omega c. So this, effectively for us, this omega here, I'm just going to write it here and then add it back up here. This omega corresponds to the omega c of gamma, right? Which is proportional to gamma squared, because omega c is proportional to gamma squared. And so then our omega d gamma is proportional to gamma, which means that d gamma d omega is proportional to gamma inverse. Right, so this is a relationship between our delta gamma and our delta omega in units in terms of the gamma itself. So that tells us that this is proportional to gamma inverse, which means that this whole thing is proportional to gamma to the power of 1 minus p. Okay, so p omega is proportional to gamma to the minus p. How does this, what does this mean for the spectrum of the radiation? Well, note that this relationship between gamma and omega. So every electron or Lorentz vector gamma produces radiation at its corresponding omega, which means from here that gamma is proportional to omega to the 1/2 power. Right, so this is the frequency at which the electron is radiating. This is its Lorentz factor, which means that our p omega is proportional to omega to the 1 minus p over 2. And so, as promised, the radiation spectrum from a power law distribution of particles is a power law, and it depends upon the electron energy index. So this p is sometimes called the electron energy index or the electron distribution index, and it's the slope of this distribution. And so the radiation spectrum that you get out also depends upon the slope of this distribution. So why does this work like this? I've done a little bit of what might look like magic here. The reason this works is that all we are doing, and there's an exercise for this on this for you as well a little later, but I'll give you the bones of that argument now, is we are adding up we're convolving this distribution with this function, and because this is sharply peaked, we are just adding up various bits of this distribution and sliding it along over here. And because this falls off exponentially, or this falls off very quickly, then the contribution from any electrons above that, the contribution to the flux at higher frequencies is negligible. And then at low frequencies, that we can ignore this 1/3 power because that is equal to lower Lorentz factors, there is a high or fast increase in the number of electrons that are emitting. So at lower Lorentz factors, the contribution is dominated by the rapid increase in the number of electrons, and at high Lorentz factors, the contribution from the Lorentz factors at lower Lorentz factors falls off. So let me rephrase that. So say you are some electrons who are sitting over here, right? And you're wondering what is the radiation power that we are emitting here. So those electrons will produce, in principle, we should at that frequency add up also the radiation from the electrons that are sitting over here. But those electrons, for them, the radiation falls off very quickly, so at those higher frequencies. And so these electrons, the radiation, the frequency at which they are radiating, that radiation does not have a lot of contribution for the lower energy electrons because of this cutoff. And then for these same electrons, how about the higher energy electrons? Well, those electrons have a shallower radiation spectrum, but because these electrons now, there are many more of them over here, they dominate the radiation spectrum at that frequency. And so that is the reason that this whole power law argument that we just sketched out works. And so this is a really crucial aspect of synchrotron radiation, which is that given a radiation spectrum, because this is observable, right? You can look at the spectrum and you can measure its spectral slope, and that will then tell you the distribution of particles. So this P, we find that P lies between 2 and 3. Typically, P lies between 2 and 3. For different kinds of shocks like supernovae, non-relativistic shocks, it actually can be a little higher than this. But for most astrophysical conditions with relativistic shocks, P lies between 2 and 3. Which means that if we just look at this expression, that this power law index here, let's call it, I'm just going to make a note, let's call this beta. So beta, which is 1 minus P over 2, then you can check. For P of 2, this is minus 1/2, and for P of 3, this is minus 1. So this is somewhere between -0.5 to, let me write it this way, somewhere between -1 and -0.5. So typical synchrotron spectra from astrophysical sources have power law indices or have frequency dependencies that are somewhere between frequency to the -1 or frequency to the -1.5 power. And that tells us something about the distribution of the electrons that are producing that radiation. Okay, so this argument is kind of a sketch, and if this makes sense to you, then that's really all you will typically need going forward in applying this to astrophysics. All you need to know is that the radiation spectrum from a power law distribution of particles is itself a power law, and the relationship between the power law index P here and the spectral index beta is 1 minus P over 2. And then regardless of what the slope is, you can back convert beta and P. If you want a little more detail, we'll talk about that in the next video, where we'll actually do the full integral and we'll determine that for all of our troubles, we'll get the same beta back. But then in addition that, when we do the full integral, we'll see the small nuances that come about by, like the argument I was making here about there being more electrons at lower Lorentz factor. Those sort of things, we can quantify what that exactly means, and that'll put some constraints on the possible values of P for which this analysis actually holds. So again, if all you're interested in doing is applying this, you can stop here. If you're interested in understanding a little bit more into the mathematics of how this comes about, let's have a look at the next video.